Hello, we are the IC Robotics Lab RoboGripper team. Our technical directors are Professor Paolo Stigagno and Professor Chenzi Yuan. Our team consists of Rory Franks and Kyle Woodward, both electrical engineers, and myself, James Nelson, a computer engineer. The University of Rhode Island Intelligent and Control Robotics Lab is a world-class robotics research lab specializing in mobile and aerial robotics, as well as multi-robot systems. They are dedicated to contributing to a better future through developing cutting-edge robotic technology. The motivation of this project is to develop a low-cost robotic hand capable of performing complex gripping functions. With the increased prevalence of robotics in modern manufacturing, repetitive and difficult tasks will soon be carried out by robots that are increasingly sophisticated. Current high manipulation capabilities come with a hefty price tag, so this gripper would be an economical replacement. Our anticipated best outcome is to have a functional prototype connected to the Rethink Sawyer arm, capable of grabbing a tennis ball and a screwdriver. Some of the key features are that the gripper be commanded from the same base station computer as the Sawyer arm, and be able to communicate grip strength readings in real time. This is a block diagram of all the key aspects of our project, leading up to our functioning prototype. Now I'll speak on the ROS integration for the gripper. ROS, or the Robot Operating System, is widely used software for creating complex and robust robotic behavior. It is used in our project to communicate between the base station computer and the gripper itself. Utilizing it will allow for easy integration with the other robots used in the IC Robotics Lab. Currently, we are using ROS Melodic in our design. ROS is also compatible with the Arduino microcontroller. By utilizing the ROS serial library, we have been able to communicate between the base station computer and the Arduino Mega that powers the RoboGripper. We have developed a unique resource-efficient data transfer to communicate all of the pressure sensor and motor position data that's needed to operate the finger. Here is a block diagram showcasing how the software works. When the system is turned on, the Arduino will start publishing data to the ROS software every few milliseconds. If the base station sends a command, the Arduino will read that command, and if it is valid, operate the motors. Otherwise, the Arduino will publish an error code. In the coming months, we plan to integrate and test our ROS system with the Sawyer arm pictured here. We will also develop a ROS-compatible data interpretation software to store and display pressure sensor readings and finger positions. And lastly, if time permits, we plan to create a simulated 3D model to test the gripper in virtual environments. Next to speak on the physical modeling and the design realization is Kyle Woodward.
The modeling aspect of this project began with the design of a basic finger in CAD software. As new needs emerged, the design was iteratively changed in order to fit them. Various aspects of the finger, such as the joints and proportions, were refined over time. The design, as of now, is shown in the picture to the right. At this time, all components needed to assemble a prototype have been designed and realized through 3D printing. 3D printing is an additive manufacturing process which constructs a model from a design in a variety of materials. In this case, a lightweight plastic. The finger was purposefully designed to not require support materials in order to increase efficiency and ease of construction. Various adjustments had to be made to the 3D printer settings of a MakerBot printer to optimally produce the completed design. In the future, the design will be further refined to increase ease of assembly by printing the gripper in fewer pieces, so less construction is needed, as well as the development of a smoother actuation of the gripper finger and the fine-tuning of the base, pictured here, to allow easy attachment to the Sawyer arm. The actualization of the gripper will have an economic benefit for the IC Robotics Lab. The gripper is low cost, being created through 3D printed materials, and easy to equip to other robots. The modular design allows for individual components to be adapted for a variety of uses without affecting the whole design. With easy access to robotic grippers, the Robotics Lab will be able to advance its study of robotic manipulation, which will allow them to attract more funding. And next, to talk about the use of the microcontroller and the assembly of a functional prototype is Rory Franks.
The microcontroller we have chosen for our RoboGripper is an Arduino Mega, which can be seen in the image in the bottom left-hand corner. The code we have written for this project has come in several stages. First, to test each component individually by writing code to observe them. We tested the pressure sensor's preciseness by using various ranges of force values being placed on the sensors to turn on an LED. And then we wrote code to test the full range of motion of the stepper motors that we're going to be using. And then once both of those were tested, we combined the code to allow us to turn the motors by using the pressure sensors Once that was completed, we then began testing the circuitry for the final design by setting up sensors and motors together through a breadboard without having them be attached to the actual finger, so we're able to test each together without having to fully assemble a prototype just for the purpose of testing certain pressure values. Once all of our individual components were tested and 3D printed, we assembled the first prototype of a finger in order to fine-tune the range of motion it will be capable of with the stepper motors. In the image, we have a finger setup with a single motor to test. The setup uses an Arduino control board, the motor control board, and the finger dock, which is there to hold the motor and the finger in place. The finger, which has a string that runs through its center and through the two rectangular attachments on the top. Both ends of the string are attached to the axle of the motor, and when spun clockwise for a certain amount of time, the string will pull the motor into a closed position, and then spun counterclockwise for the same amount of time, the string will pull the finger open again. Future tests complete with the microcontroller include refining the Arduino code to utilize the data from the 7 pressure sensors we plan to use, and having them control the 6 motors that allow the hand to open and close smoothly, to keep a grip on an object that isn't so hard that it crushes the object within its grasp, or it's so light that it drops it onto the ground. Then, once we complete this, we're going to attach it to the Sawyer arm and have our code run through the base of the Sawyer arm to the Arduino microcontroller with the gripper. And then we'll begin testing the gripper attached to the Sawyer arm and holding objects suspended above the ground on the arm, maybe about 2 feet above. And once we finish testing this, we'll look into using an XB wireless device to connect the Sawyer arm control panel to the Arduino to reduce the amount of wiring that will be necessary for the gripper. To summarize our accomplishments towards our anticipated best outcome, we've designed and printed functional fingers and the RoboGripper base, successfully written code that controls motors and pressure sensors, the ROS correctly interfaces with the Arduino, and we've also assembled a full functional finger prototype. To summarize our key future technical accomplishments, we will need to completely assemble the RoboGripper and attach it to the Sawyer arm, combine the software for the motors and the sensors, have ROS integrated with the base station of the Sawyer arm, and test the gripping of several objects. Lastly, we would like to thank our technical director, Professor Stegano, for his invaluable assistance throughout this whole project, and Dr. Sunak for guiding us through the capstone process.